Yeah, great. Okay. Okay. So I had this whole thing prepared, thinking that Andreas and I were the same age. It turns out actually he's a year older than I am, and so that whole thing didn't work out. And I'm thinking, how did you grow up so quickly? Okay. So he's always looked so youthful that I would not have assumed he would be a year older than me. But for someone who has worked on liveness, the kind of defining feature of Andreas is that he's never satisfied. He's never really feels like he's gotten to the goal. It's always something else. So I assume it'll be the same way even at this stage in your life. It's always going to be something else. So that's one. The talk is really about theorem proving and living in a theorem proving universe. It kind of touches on many of the themes that people have already spoken about earlier today. It's actually a bookend to Doug Bayer's talk. I'll be saying the opposite of what he said in many ways. How many of you here have not used a theorem prover? So, okay, just one person, that's good. So you kind of know what I'm talking about. And what I'm talking about in this is really an extreme version of this. That is, if you get inside a theorem prover, stay there, never leave. Okay, do everything you can, everything that everybody talked about today, just stay within a theorem prover and do that. Now, I've given the exact opposite talk also. I've given the other version of it, which is break everything down into individual pieces and reuse them. And reconciling the two is a large part of the challenge in doing this. But in this talk, I'm advocating staying inside a theorem prover and working with it. So I got into theorem proving more or less by accident. I actually was hoping to study AI, but the only part of AI that I really understood and liked was theorem proving. And so where I was studying was actually a great place for this. And this theorem proving subject looked like it was sufficiently obscure that no one would actually trouble me, that I could literally toil in obscurity working in theorem proving. This would be a very comfortable place for me. And when I said this once, Lenore asked me immediately, so how is this obscurity thing working out for you? It's been working out great, thank you. Okay. I have no problem with it. All I need to do is really just shut up and program. And so the thing that's been happening is that in the 80s especially, there was a lot of great activity in theorem proving. And formalization really became in many ways it wasn't a solved problem, but it was clear that it was a solvable problem. And this is what the work that we did in the 80s provoked Boyer to proclaim that no one's ever going to say this can't be formalized. In contrast with what DeMilo, Lipton, and Perlis said about if mathematics were one of strict logical, if the mathematical process were one of strict logical progression, we would still be counting on our fingers. Proving things like the incompleteness theorem is way, way beyond counting on your fingers. Please. Mm-hmm.
But that was long before the criticism they invented it.
Well, Alan Turing probably came up with inductive. Euclid came up with inductive. Mm-hmm. Yeah. Yeah, it's all gone. Yeah, that's right. Mm-hmm.
And nobody seems to. Everybody remembers his critique.
Mm-hmm. Yeah.
Nobody remembers that he was poor before he became again.
Right. Yeah. So, so the idea then is really about doing formalization well, making sure that you can actually capture the mathematical structure, the mathematical beauty, and make it so that it's automated in a nice, facile way that brings out a certain level of understanding and insight that the human being can extract from the automation. So supporting the human being in this process is really important. Being able to converge on the mistakes in your formalization, and there are going to be hundreds of them. I make mistakes virtually every few seconds that I type. I get something wrong. It's really hard for me to get things +1 or -1, and this is something where the automation, the theorem proving really helps me a lot. So for me, logic is the study of the interplay between language, meaning, proof, and computation, and this is exactly the defining drive of Andreas's work as well. It's exactly this interplay that he's been studying with contributions to all of those topics out there. And so the question for this talk is really, should we replicate Andreas within a theorem-proving universe and make sure that all of these things can actually be done inside a theorem prover, not with a theorem prover, but operating inside a theorem prover. I'll answer the question at the end. The history of this goes back a long ways. It goes back to a guy called Ramon Llull, who talked about reducing all knowledge to first principles. This was not something new. I mean, Aristotle had talked about reducing all knowledge to first principles as well. But what Ramon was talking about was developing a symbolic notation and conceiving of a reasoning machine, some way of mechanizing it. And he was a kind of a religious scholar. So what he wanted to prove was certain religious precepts could be established by reasoning. And the Pope wisely said, if you apply rational thinking to religion, you're confusing faith with reason, and condemned his teachings. I feel like in the same situation. When I say these things, I feel like many of you will have the same reaction as the Pope, that I'm confusing theorem proving and pragmatism. And so you guys might play the same role as the Pope. Ramon Llull, by the way, is also the founder of social choice theory, it turns out. I found out from a talk that Phocion Colaitis was giving. The second big person in this was Gottfried Leibniz, who talked about having a universal language for expressing concepts and a machine that could essentially crank out the truth in this universal language. And he was quite lyrical in proclaiming what this would get you. So what must be achieved is in fact this, that every paralogism, something that is kind of like a logical error, fallacy, be recognized as an error of calculation, and every sophism, some way of actually reasoning deceptively, be expressed in this new kind of notation, appear as a solecism or a barbarism. That is, it should look like a grammar mistake. When you try to pull a fast one in terms of the reasoning, it should look like a grammar error, to be corrected easily by the laws of this philosophical grammar. Once this is done, then when a controversy arises, disputation will no more be needed between two philosophers than between two computers. Computers is, of course, people, human beings doing the computing. It will suffice that pen in hand, they sit down to their abacus and, calling in a friend if they so wish, say to each other, let us calculate. So this was kind of Leibniz's kind of glorious vision that he had all that while ago. And none of this really came to fruition until roughly the middle of the 19th century, when the age of reason really started with someone with, say, George Boole. It turns out Hermann Grassmann was a big figure as well, Richard Dedekind, Giuseppe Piano, Gottlob Frege, Charles Sanders Peirce, and so on. So the 19th century was a big deal. But the mechanization of automated theorem proving really started with Martin Davis programming a Presburger arithmetic procedure. And this was an interesting quote. Its greatest triumph was to prove that the sum of two even numbers is even. Try typing that into one of your theorem provers and see if it does it. Okay, that's not something to be embarrassed about. Whereas I think many modern theorem provers actually do leave a lot to be desired. So the kind of development, I'm missing out on Noel Shaw and Simon and Hao Wang and Davis Putnam and many others, but focusing more on the proof checking branch of theorem proving, which is started with John McCarthy, and later on De Bruyne picked up the mantle with Automath. Woody Bledsoe is actually a pioneer in automated proof checking. He was the person I learned theorem proving from in the first place. And when I was doing my thesis, he told me that he had actually done a major proof checking project. And he checked Morse's set theory book. But it only came to light recently that there is actually a record of this. There is a Sandia report on the project that Woody Bledsoe did. And it's a reasonably impressive piece of proof checking. The big kind of revolution in theorem proving was really Bob Boyer and Jay Moore's theorem prover for pure Lisp. This is what actually made a lot of what we can dream about now possible the kind of 40, 50 years ago. So this was a theorem prover they developed initially at Edinburgh, then mostly at SRI, and that's what I did my thesis on. The LCF approach, due to Robin Milner, is also a kind of dominant strain of proof checking. So going back to this Boyer-Moore theorem prover, the current version is called ACL2, and the logic that it supports is pure Lisp. It's essentially applicative common Lisp, and you can write, for example, a function like reverse of x, and this kind of thing. You can append the reverse of Kerder of x with the singleton of the car of x, and the theorem prover automatically proves termination, that it shows that this terminates. And then you can give it a theorem like this, that the reverse of x is equal to x, and it proves it automatically. This is the only formula I really have, I think. I don't think I may have a few others, but the theorem prover is magnificent. I mean, it proves, it picks the right induction, brings in the right lemmas, the rewrite rules, and in the proofs I was doing, these were enormous. I mean, the chain of rewriting that was needed, because there were layers and layers of formalization going on. The theorem prover was truly magnificent in doing this. And just to give you an example, one of the proofs I did was the Church-Rosser theorem. And initially I had a lot of difficulty with it, but then Boyer suggested that I use the De Bruyne representation, which I didn't know what it was. When he finally told me about it, that was exactly what I needed. And in a single night, I was able to actually do the main part of that theorem. That is, once that's done, you know it's there. And this is a proof that people have struggled over for decades. So this was quite a big deal to be able to do a proof like that in a single night. And today you can take PVS and you can actually, in a sitting that is in 30 minutes to 1.5 hours, you can prove a major theorem. That's not unreasonable. You should expect to be able to do that. The NASA lib has a bunch of major theorems, and when you ask the people how long it took them, they said lunch. Okay, that's how long it took. So this is something that you should be able to do. The Jens's 16,000 line proof was monumental. I think that's really something where it takes tremendous concentration to pull off something like that. So the thing that this led to is this notion of what I call the computational Sapir-Whorf hypothesis. That is, language formal language impacts the way that you can formalize and automate reasoning. This is not widely appreciated. It's not the case that you can just take any language and layer automation on top of it. It really, good automation comes from the features of the language kind of exposing certain reasoning possibilities. And so Church's higher order logic is a good example of this. It's adequate for doing virtually all of math, and it's almost entirely executable. So this is something that you can capture, and many systems are actually based on higher order logic. And PVS is an instance of this. Whoops, the thing is cut off here. I compressed the wrong thing. But the main thing I want to show here is that the kind of interplay between language and automation that I'm talking about really comes to the fore in the way the type system works. So here you can have, for example, types like the factorial returns posant. And that's something that if you didn't have that cached as the type of factorial, it would be a pain, because the n choose k, you're going to use factorial as the denominator. You're going to use the product of factorials as the denominator. So that little bit of type information, knowing that it's positive, that the product of positives is positive, helps you say that the denominator is not going to be 0. And it cleans up math. It actually adds a lot of clarity to computation as well, because a well-typed program now, unlike Milner's claim that was false for ML, a well-typed program can never go wrong. Okay, it can only run out of stack, or it can run out of heap. Okay, that's a significant win in terms of a clean property that you get. This example of n choose k that's hidden there was interesting, because I claimed that it was an integer, that it was actually when you take n choose k, that you get a positive integer out of it. Unfortunately, the definition on the right-hand side is obviously a rational number. Okay, and so the theorem prover says it's a rational number, but show me that it's an integer. And you can go back and look in math book after math book after math book. This basic fact is missing. And it's no less trivial, it's no more trivial than the facts that they do establish. And this is something that's missing, and math expositions are filled with these kinds of errors. So you'll find at least one in every facing page. The other thing that's kind of been important is having large libraries. And this is something where I think Lean is doing a really remarkable job in getting mathematicians to fill out this thing called MATLib. So that's growing pretty rapidly. So the other systems also have large and growing libraries. So this is, again, something that would be a burden for you if you were building a bespoke tool for your particular task. So having these libraries is actually a big win. And having these libraries centralized around a single theorem prover is a useful thing to have. So this, to build some new inference system and try to bring in these libraries would be a huge amount of work. There are just like hundreds of man-years going into the development of these libraries. Okay, so what can you do inside a theorem prover? The first thing is obviously you can formalize, and I assume many of you had the experience that just the mere act of formalization reveals a bunch of errors. Just writing the definition of n choose k forces you to think, why is the right-hand side a positive integer? So it forces you to think about that. So that's one kind of thing. The other is kind of modeling. So unlike a programming language, formulas don't need to be executable. So you can write models that are not non-executable. You can also write models that are executable. And you can write them at varying degrees of efficiency. You can write models of the physical world. You can write models of human beings. So these kinds of things are really helpful in developing software, because software does not operate in a vacuum. You do need to know the models under which you're operating. You may have, for example, models of computation, models of communication. You may have physical plant models, fault models. So there's a whole bunch of these that you can capture of these. And this is something, again, that has been a popular activity in theorem proving, which is that you don't just model the program under analysis. You model the full environment and you prove properties under that environment. Then you can go further and do proof. And proof is a very, very efficient way of finding mistakes, both in your formalization and in the proof itself. So you can correct your reasoning. And you can use a theorem prover in many, many, many creative ways that these bespoke tools do not support. So you can use theorem provers for exploration. You can use them to kind of just do symbolic execution, for instance. You can use them to find abstractions. So there's a whole bunch of things you can actually do creatively with a theorem prover. Now, many of you claim to have used theorem provers, but I don't know whether you really truly exercise your imagination in using it. But if you do see the possibility of using the theorem prover in imaginative ways, you'll find that it's really mind-blowing what you can do with it. So you can use it for simplification. You can use it to do rewriting and symbolic execution and so on. This is, again, something where you can, if you wanted, use a theorem prover as a backend, but you can actually use it as kind of like a kind of computer algebra system. You can use it for constraint solving. Byron's talk was about this, about SAT and SMT solving. So you can generate both counterexamples, test cases. You can check for validity of formulas. So this is, having this kind of automation is really helpful for a number of applications. In fact, it would be quite difficult to do this without this kind of automation support. And this is what PVS actually, we intended it as a theorem prover that you lived within, but a lot of people are using it as an SMT solver because that's all that existed at that point. And then we slowly started kind of pitching out the SMT solver part of it in the 90s. So we started providing standalone SMT solvers. But if you look at the work on predicate abstraction, for instance, it was done directly using PVS as a SMT solver by Suzanne Graf and Hassan Saidi. So you can embed other logics. Again, we did a bunch of these in the 90s, and we're still doing work like this. You can embed other calculi. You can embed programming languages. You can embed programming language semantics. You can embed modal logics, deontic logics, cryptographic protocols. So a lot of these things you can do with different degrees of shallowness. So that by shallowness, it means really how much of the syntax of the target logic are you capturing in the host logic. Okay, so in the host logic, that's the degree of shallowness. And the more you capture, the more meta theorems you can prove. That's the idea. So the more ability you get to prove meta theorems about it, but you may not want that. So you can construct abstractions. You can do this automatically. I mentioned the work on predicate abstraction already. You can formalize static analysis as a lightweight theorem proving exercise. And finally, you can program, and you can program with efficiency, with correctness, and you can get both low-level and high-level code out of it if you wanted. You can program down to the machine code level if you wanted, or you can program in a very, very high level if you wanted. And so you can you get this full spectrum of abstraction. So in the end, what we are engaged in, the activity that we're engaged in, is something I call abstraction engineering. And in abstraction engineering, you're looking for certain sweet spots where the abstraction actually buys you a lot in terms of the properties you want and the facility with which you can derive those properties at this abstraction sweet spot. So it's not about more or less, it's about a sweet spot in the abstraction. And that's what you can get with these theorem provers. So how much time do I have left? I need to maybe hurry up. Okay, that's not bad. I can do that. Okay, so why would you do this and not the other thing, which is just use a theorem prover as a backend tool, and that way you can call perhaps a model checker, an SMT solver, abstract interpreter, type checker, all of these things as backend inference tools. Why would you not? Why would you do the idea of living inside a theorem proving universe instead? And the kind of thing that you get is that the outside world does not make sense. Okay. It doesn't even try to make sense. Okay. In a theorem prover, if it doesn't make sense, you're not going to be able to prove theorems, because that's part of what you get out of it. And doing a proof, you understand. Okay. So that's a kind of important point about the use of staying within a logic and embedding all your needs within that logic. So logic is also a good way to communicate. It's really hard for people to read code, for instance. It's who knows how people interpret it. Whereas logic is actually something that's both machine-friendly and human-friendly. It forces you to think in a way that just writing and running code does not. Although you can write and run logic as well. So the theorem provers catch lots and lots of errors. They allow you to shift abstraction layers in a way that sometimes your bespoke systems don't. They don't support this. You can deal with both computable and non-computable models. You can model the physical universe as well as the virtual universe in proving properties that are of interest. And you can actually use logic as your lingua franca for what all your tools actually speak. They communicate in terms of the core logic. So that's something that is really an advantage, because often there are semantic impedance matches when tools actually communicate different things. So by integrating these tools within a single coherent logic, you make things a lot more unified and seamless. So the limitations, though, and these are serious limitations. There are good reasons why I can speak through the other side of my mouth as well. Okay, which is that proof is not for the faint-hearted, and this is not. It's not as insurmountable a barrier as you might think, but it does take, I don't know, a few hours to a few days worth of training to get to this point. So I have lots of undergrads doing this stuff, and they are actually much better at doing proof than I am, and they get there very quickly. So it's not insurmountable. It's just that we've not done a great job of teaching people that this is a worthwhile activity and they should get good at it. State and interaction are not easily modeled. So when you generate code from PVS, for instance, you can generate C code, and it is stateful C code. It is going to work just the way your handwritten code would work. Okay. But you can do much more expressive things in PVS that if you were to handwrite in C, you would spend a long time trying to get it right. In fact, you would probably never get it right. But in PVS, it would be no problem to write it and generate the C code for it. So there's certain things where programming language or a bespoke system gives you more freedom than you would get. There are certain kinds of data types that are hard to capture in a logic, but that you can get away with in a programming language. Because a programming language does not have to make sense. A logic does. In applications such as optimization, you sacrifice soundness. And so this is kind of something that's hard to do in theorem provers, although as Byron said, you can have a switch that gives you a little bit of unsoundness. Sometimes that's useful. It's not a bad thing to get to some results quickly. But in general, you would have a soundness problem. The other challenge here is that proofs are another artifact to maintain. That is, in addition to the code, you're maintaining the proofs as well, and that's usually been a challenge. And so it's really hard to replicate the ecosystems that programming languages like Python and Java and C include. So they come with everything. So this would be a huge amount of work for anyone working with theorem provers. And the reason we build bespoke tools is that we can actually take advantage of some of the optimizations afforded by the narrowness of the domain. So that is something that we can take advantage of, that sometimes it's hard to do in a system as general as a theorem prover. So these are serious challenges. So yesterday it occurred to me that I had actually made this case a long time ago. Sometimes you forget that you've actually said something before and you could go back to it. So in 1995, I gave an invited talk at the Mathematics of Program Construction, and I wrote a paper called Computer-Aided Computing, and I made pretty much the same points then. But on the other hand, we've actually spun out the SMT solving. We've developed a whole series of solvers leading to Yikes. We've spun out the model checking. We used to do that inside PVS first. And so there are kind of lots of reasons for doing this. And particularly, this is what people asked us to do. So we ended up doing some of that. On the other hand, now I believe that we should not have done that. We should have gone for the long view. We should have stayed inside the theorem prover. We should have developed much of this inside the theorem prover. And one of the cases for this is made very beautifully by Cesar Munoz and John Rushby, in which they showed how they built a system called PBS, where they embedded the B method in PVS. And it's only like about 25, 30 lines of PVS. You get something that's actually better than the B tools. Okay, so you can leverage PVS as a kind of universal proof obligation generator. So it generates the refinement proof obligations just by writing the right formulas. In the festschrift, I show this for Floyd's method. You can adapt it in many other ways. So that way you get all of this automation and theorem proving that you have. At the same time, you're operating as if you built a bespoke tool, because it's generating the same proof obligations that a system like Daphne or Boogie might generate. In fact, one of the things I have done is captured the Boogie memory model in PVS. And again, it's like 20, 25 lines of code. It's literally minutes worth of work to do this. I did it while Peter Muller was actually talking. So it's a very simple thing to do. And the amount of stuff that the theorem prover gives you to do this is hard to replicate. So the nice thing about this kind of integration is now anything that you bring in is automatically usable within this framework. It's kind of semantically seamless. So that's the important advantage that you get by staying inside the theorem proving universe. So this is achievable. The systems that we have are entirely capable of doing this. And if 30 years from now, just like engineers stay within MATLAB, I wouldn't even say 30 years, I would say less. I'm being very conservative in my predictions. But if you're staying within a theorem proving framework, you shouldn't be surprised, because just like MATLAB gives you these advantages of staying within one framework and doing all your modeling, we can get theorem provers to a point where they give you the same advantages. And so there's quite a lot of work to build on. And in particular, you can reason about theorem proving itself in a theorem prover. So that's something that started with Boyer and Moore's meta functions, and there's kind of a nice tradition of work doing that. And we kind of can already generate efficient code. There's really no reason to write code directly. If you write it in a theorem prover, you can get good code out of it. You can get code that's memory and type safe, as I mentioned. And the other thing is that we are beginning to model a lot of things. So you're getting these models of a lot of the artifacts that you might need to work in this world, just like you would with MATLAB. So that's something that I think is happening. And we're figuring out how to extract logic from natural language as well. So this actually was another prediction that Vannevar Bush made in his monumental article, As We May Think, which heralded the modern world. And in that, he actually has two riffs on theorem proving. And in one, he says logic can become enormously difficult and would undoubtedly be well to produce more assurance in its use. We may someday click off arguments on a machine with the same assurance that we now enter sales on a cash register. So that's, he expected that theorem proving tools would be just a part of a scientist's workbench. So conclusions, the main message that I've repeated over and over is that we can go back to this Leibniz dream and think of logic as a universal formal language in which we can integrate a bunch of inference tools, embed a number of programming languages and calculi in a semantic form, and carry out proofs at scale. Not just proofs, but a lot of other simplification, abstraction. A lot of these operations can be done. And the last 40 years have actually yielded a number of impressive advances in automation. We heard a lot today about Andreas's work with his colleagues, and that's I think something that we can build on. And it's a kind of you can create an ecosystem where you have it vertically integrated. You can reason about everything from hardware all the way to the distributed systems and perhaps even user interfaces and so on. So this opens the door to sitting inside a theorem prover and operating with all of these models available to you. So you can imagine that you can reason about human cognitive models, you can reason about cyber-physical systems, you can reason about the combination of these things, and essentially make the world safe in a way that would be hard to do if everything were fragmented. So, to answer the question at the beginning, since Andreas has cracked the meaning of life and slayed the halting problem, he shouldn't live inside this universe. He should, I think, be in charge of watching over it. So that's the position I think I would reserve for Andreas. But the takeaway is never leave the comfort and clarity of a theorem prover. Thank you.
Any questions for Shankar?
Well, suppose somebody wants to start now using Theorem prover. There are several alternatives. What would you advise him? I mean, Koch or yours or Isabel Hall or I don't know. And each comes with
mine who passed away, Drew Dean.
Huh?
So he said use the one that the person in the neighboring office is familiar with.
yeah, that is so good. No?
So it's really important to have access to experts.
Yeah.
I recently ran a boot camp, and it's really sobering to see what the students struggle with all of these systems, by the way. I find many of them actively dangerous. If you get people into these things too early, their mind gets frozen into this pattern of thinking, and then it's no longer math to them. It's whatever that system is. So the key thing here is that you really have to have a certain level of mathematical maturity before you start.
Shankar, can you use the mic? Otherwise, everyone.
Yeah.
I think I'm next, right? So, well, first of all, a correction. I didn't say we should have an off switch for soundness. That was Rupak's idea. I actually am quite religiously opposed. Like soundness is something I've actually had to push on very, very hard. So I think I'm adding.
I didn't say you advocated it.
Okay,
I said
okay,
you
yeah,
mentioned
okay.
it. Yeah.
Tell me your thoughts on this sort of trend where people are training large language models over proofs, potentially to make an assistant to help you use these provers. And does that because now this gap around you need to sit. Basically, your answer to the last question is you need to sit at SRI next to people who know how to use the tools, right? But maybe now with the large language models, this world is actually not far away from us. What's your opinion there?
No, it's still quite a distance. So the people for whom this actually helps a lot are those with considerable mathematical maturity already, and it really is not something where the kinds of problems novices run into, the large language models don't address, because that's such a wide space. They address things where people have gone deep, and that's why you have more data. And so the experts somehow find value in this because they are operating in the same space as the training data, but novices really just hit a roadblock and they're not able to make progress. The other thing here is that I'm not so confident that the results people are claiming are actually things you would see in the wild. In fact, you don't right now. And I suspect it's in a large part because they're not able to separate out the training and test data. So you're seeing there are lots of similar proofs, there are lots of cut and paste things, so you end up duplicating a lot of the training data and the test data, and that's why I think you're seeing numbers that don't get borne out by things in the wild. Having said that, I think that a lot of the activity in doing proofs is, I mean, some of it is high entropy, a lot of it is low entropy, and if these language models can capture the low entropy stuff, they really do relieve considerable burden.
Do we have any last question for Shankar? Andreas?
So it's somewhat related. You mentioned the inference of logic from natural language.
Yeah.
There is this gap, right, between the so
informal gap. Yeah.
What do you do about it?
Yeah, so this is, I think, a serious burden for all of us who work on formal methods, that the number of papers written on how you ask even experts to interpret temporal formulas, they can't tell you what these temporal formulas mean. And quite often I find myself proving something that isn't what I intended to say. And so the kind of approach to this is, you can think of it as a multimodal approach. So on the one hand, there are stakeholders for whom natural language makes plenty of sense. There's a certain interpretation they have of it. There are people who can read the formulas. There are people who can read the examples, scenarios, turning the formulas back into natural language, generating models so that people can look at the models and see if this is what, or visualizations. So all of these are helpful devices for bridging this formal and informal gap. But we need to go both directions in order to do this well. So we need to be able to take formulas and render them in natural language, and take natural language and render them into formulas. So there is a system we built called Arsenal. We built 2 versions of this, and you can go to GitHub and try it out. It's kind of, it's a pre-LLM model. It's only now that we're actually doing it with more with LLMs. But
So to extract logic from natural language.
yeah, but you can go the other direction also. So what it does is it reformulates it so that you can check, a human can check that the, even someone who can't read the formula can check that the interpretation is right.
Thank you again, Shankar.
Yep.